Hello, this is Britton LaRoche. I'm a senior solutions architect located in Plano, Texas. And presenting with me today is Andre Spiegel, who is a distinguished engineer at MongoDB. We're going to be talking about single view at the push of a button. So in the topic today, we're going to cover single view customer use case, a specific one that we designed this application for. We're going to talk about why we chose to go serverless versus some other method. And then we're going to talk about specifically how do we master the data. And then we're going to do a demo. And as this is a recorded session, we won't have time for questions and answers. But we hope that we were able to provide some sort of information for you in the deck and in links that will follow with source code. So use cases. We're going to talk about here some of the single view requirements from real world companies. And in general, protecting customer data and complying with privacy laws is not an easy task. The California Consumer Privacy Act is something that was put in place in California to protect consumer data. And it gives them two primary options. One is to be able to be notified or at least be informed as to how the private data is being used, who it's being sold to. And if they don't like it, they have the option to opt out. Should the company in question not comply with their requests, they do have the right to take legal action. This is the timeline for the California Consumer Privacy Act. And this, like many other states, privacy has become a concern, and this is how California addressed it. In January 3rd of 2018, the CCPA was introduced into legislation in California. In June 28th of 2018, it was actually signed into law as part of the California Civil Code. Now, it didn't become effective until January 1st of this year. And July 1st of this year is when the Attorney General can actually start to take action against companies that are out of compliance. So this is something that a lot of companies are scrambling to produce, to keep up with. In many cases, most of this effort is going to be manual. So there's a number of key problems facing customers that are trying to protect consumer data. One is, how quickly can these companies respond? In other words, how do they find this data and create an application that would scrub it across multiple systems? How are they going to do it in a timely fashion when a customer calls in and says, I need to remove my data? How are they going to comply with the CCPA and other privacy laws? And how are they going to protect their consumer data from a breach? So privacy and security are of utmost importance. The other interesting thing, the problem about this is, how do you match a customer across multiple systems? And this is where a single view use case came into being. And then being able to opt out quickly. When this customer decides that they want their data removed, how do you actually manage to do that in a timely manner? These are the key problems that most companies are facing these days. So let's take a look at the four key challenges. One is that customer data exists in multiple systems. The second is that there isn't one unique identifier across these systems. If we have online sales and service, marketing and shipping, there isn't even a standard way of identifying. Is it customer number, customer ID? How are you identifying it? And then if you look at it, each unique ID is different across the systems, but identifying the customer without the unique ID is difficult. We've got first name, last name, address, maybe email address, maybe phone number, maybe date of birth, maybe one system has information that another doesn't. How do you identify this customer across multiple systems? And the last thing is that each system has data in different locations. It could be in multiple tables. It could be in log files. It could be in invoices. It could be in many different locations that you have to go and remove that data to be thorough and to be cleansed in every single system. So one of our customers, this is an actual use case, they had over 300 disparate systems where they had to go in and scrub that data. And they looked at, how would it be done if they were to do it manually? It would require 10 full-time DBAs. And their only job would be to identify and remove customer data that wanted to opt out. And this is based on a little bit of a science to figure out how many customers do they think on average would opt out, or based on complaints that they had so far. And the manual effort for these guys to work full-time to do this would be about $14 million a year just to scrub data out of the systems. The time required to cleanse these systems, because they would have a full workload, and they may be slow at getting to all the systems, and it may take quite a bit of time to get all of the data for each individual customer removed, may lead to a lawsuit because they weren't able to act quick enough. So the solution for this customer was to have customer identifiable data moved to the single view. In other words, all that would remain in this particular online sales system would be the customer number and an array of orders. All the different orders would be there. So all the transactions are maintained and the customer ID is maintained. The master record is created across all of the systems. And so we can actually see that this system A is still here with all its data preserved, but so is system B, C, and D. All these systems are here. And when the system of record, when you're looking at this, you can see what is considered to be his current mailing address and his correct name. In some cases, it may be Jimmy Bond, Jim Bond, JW Bond, but James Bond is his actual name. And this is the single view that has all this information. So this data was mastered, and all of these records from these different systems were pulled together into one master record. We still kept all this information. So we're keeping this as an array of subdocuments within one master document. So at any point in time when I get the master document, I can still see all the information that corresponds to a specific system. If I need to get the shipping address, I can actually look up the shipping information based on the ID and know that this is the address that he wishes to ship to. The last thing that's important about this layout is that there's only one place to remove the data. Instead of removing it from 4 different systems or however many hundreds of systems, it's just one system that has all the information. So it's one record, one document with multiple records that are scrubbed. And that is a very simple way to proceed. So the solution requires real-time access to a single view, right, across all of these systems. And what's important about this? 2 things. Primarily, scalability and security. So the microservice REST API, if we're shipping packages in real time, it needs to be able to look up the information and find this person's name and mailing address in real time. We'll be able to query the system and get that information back as soon as the shipping label is printed. This should be incredibly fast. What that means is this REST API that's making this call has to be scalable. As the workload increases, this REST API needs to be able to scale with it. In addition, the backend needs to scale. So if there's a Christmas rush, then the database backend also needs to be able to scale. So it should be auto scale as well. And these are the things that are important to the customer: a scalable REST API and all the functions that are getting this information in the database backend. The last component is that the data must be secure. It needs to be protected. So performance and security are the 2 main criteria for this to be successful. If we took a look at security, if we take a deeper look at this, if we go to mongodb.com/cloud/trust, you're able to see all of the compliances that we have and certifications that we have passed. And it's safe to say, because this has been rigorously tested by third-party providers, it's probably safer to put the data in Atlas than it is on an on-prem database, and much safer than most third-party cloud databases. We are HIPAA compliant, GDPR compliant, SOC compliant, US Privacy Shield compliant, ISO IEC 27001:2013, so ISO 27001 certified, and PCI DSS certified. And this was one of the hardest certifications to get. We have gone and completed this, and you can go here to cloud.mongodb.com, download our security white papers, and in many cases, actually see the certification and the third-party test results, all from this particular website. So why serverless? Why did we go serverless? And the primary answer is that we wanted scalability without maintenance. In other words, we didn't want to have to go in and manually ramp up the servers and the database backend. We wanted to auto-scale and to auto-scale down. So you're only paying for what you use. So the way this works, this is the MongoDB serverless single view architecture that we put in place. Again, we're providing the source code to you so you can actually see how this works. Source systems are able to interact with MongoDB. These are the source systems A, B, and C through a REST API. This REST API runs on a set of servers that scales up as needed. Say the Christmas rush is coming and it's on one server, it can scale to 2 or 3, and then scale back down as needed. All of these source systems can access the data in real time, and as traffic increases, so does the scalability. All of this logic to match and update and do the mastering of documents as they flow in real time from source systems is located here, and they run on each one of these servers as it scales up and scales down. So we have functions and we have triggers that allow us to take source data and master it into a master collection. This data is then replicated across all maybe different availability zones or even regions if necessary. So this is auto-scale capability. This also is auto-scale. Atlas has the ability to scale up and scale down as needed automatically without intervention. So both the front end REST APIs and the back end database service can scale. The nice thing about this is all of these functions are outside of the database. So you have two different processes going on. A lot of computation here and a lot of data processing here. In addition, we don't just have a REST API, we have an SDK that allows you to query the database through a website, which can be hosted as well, and it can run on these servers. So the website, the database backend, or the admin console backend can be scalable and serverless as well. So serverless gives you 4 key features. 1, auto scale. 2, no maintenance to do that, to go in and have to have someone maintain and monitor the database. This is handled for you. High availability is built into the solution. So at any point, if there's a failure, we have other nodes to take over. And then microservices, it opens the door for independent operations to run on their own individual source code. And not rely on any one particular component. So the ability to start microservice development and to create REST APIs and then consume them across multiple microservices is open in this architecture. This is the reason that we went serverless. There is no application servers to maintain. There is no database servers to maintain, and that you have to actually go in and scale up and scale down manually. So let's talk about the different pieces that we're going to show in the demo and the different pieces that we provided for this solution. There's a serverless website, and the admin console is hosted in serverless. And it has an SDK, a JavaScript SDK that allows you to actually authenticate to the database and make queries. And using nothing more than dynamic HTML and CSS, provide the information of this customer across the multiple systems. In addition to that, we have a serverless REST API where you can actually make requests against the database and get the data back in real time and have that auto scale as well. The nice thing about this is this increases developer productivity across multiple microservices. All they need to know is the REST API. So if a developer knows REST, JSON, and that is pretty much all they need to know in order to access the system. They don't need to know a complicated query language or anything of that nature, just REST and JSON, and they're ready to use this serverless application. In this particular case, we've created a REST webhook, and we've passed in the first name and last name, and then we've returned a document which has an array of values for the sources, the source systems that are out there. The opt-out in one step is a powerful feature. You simply put in an opt-out flag set to true, and this data will be scrubbed from the system. And the way that looks like, and again, this is what the source system would retrieve, is all of the unique IDs, so you're able to identify the customer if they have an account ID across all their systems, but all the customer identifiable privacy data has been removed. No emails, no name, no gender, no demographic information. It's completely scrubbed, and it's done so very quickly in one step. So what we're going to do now is we're going to go into mastering the data, and this is where I turn it over to our distinguished engineer, Andre Spiegel. Thank you.
Thank you, Britton. So we're now going to talk about the algorithmic heart of the system. This is the component that actually masters the data. So how do we find out that two people who look very similar are actually the same person? The way we're doing this is shown here in the subtitle. We do single linkage clustering. That is not rocket science, and that is not something that we invented. You can actually look it up on Wikipedia. It is a mechanism to solve exactly that problem. However, we're doing it in MongoDB, and we're doing it with Stitch. And I hope to show you that this is a particularly elegant way of doing that. So, what is it about? We want to find out whether documents are similar. And the way we do that is we need to define some kind of distance relationship between documents. We got documents that are very similar, and they get a number, a distance of, for example, here 0.02. And then we have other documents that are a little bit further apart, and they get a larger distance of 0.3 in this case. And once we have identified the distance between each pair of documents, we can actually cluster them together and say these two documents on the left-hand side are probably the same person, and these three documents on the right-hand side are also probably the same person. That's the whole idea. Measure the distance between every pair of documents and then cluster those that appear to be closer together. Now, what do we need in order to build that? First thing is we need to have a schema design, and it turns out that it is actually very elegant to do this in MongoDB, way more elegant than, for example, in a relational database. The second thing is we need a distance function. We need to actually find out how far two documents are away from each other. And finally, once we have put documents together, we need to find out what the truth is. We may have different variants in spelling and what is the actual correct value. So let's start with the first one, schema design. We start out with a bunch of documents, not particularly complex in this example. We have records that are key value, very straightforward schema, and they seem to represent kind of the same person, right? It's James Bond here, and Jim Bond, and James Bondy, suspiciously the same. So once we have found out that these are actually probably the same, we want to turn them into a different data structure, and that's here on the right. We have one document where we have an array of source documents. These sources all belong together and are the same person. And from this we can synthesize the truth. We figure out that the real name is probably James Bond and the date of birth is the 17th of August 1967. So this data structure is actually pretty intuitive. I hope you will agree with me on that one. And I have seen relational systems that try to do something similar, and people would tell me, we don't know which table is which. I don't think you're going to have that problem here. So this is the kind of schema we want to build. And the next question is, how do we find out this distance between documents? So what we need is a function that takes two documents, A and B, and turns them into a number between 0 and 1. 0 means these documents are actually the same. 1 means they couldn't be more different. So how do you figure that out? Actually, we tried fancy stuff. Things like locality-based hashing, machine learning, all sorts of different things. And it turns out that these algorithms need a lot of resources for only marginal benefit. Simple goes a long way. We ended up using the Levenshtein distance between strings. It's the number of edit operations you need to get from one to the other. For example, if you have Bond and Bondy, it's one edit, adding the Y to get from one to the other. So that's a Levenshtein distance of 1. And the smaller the Levenshtein distance, the more similar the strings are. So what we use in our system is the normalized Levenshtein for every string attribute in two documents with adjustable weights. Some attributes are more important than others. This, however, is only the default. You can provide any distance function between two documents that you come up with. Simply plug it into our module and you can use that. So the next thing we got to think about is this. We would like to compare everybody to everybody, but that won't work. If you imagine you have 1 million customers and you want to compare 1 million to 1 million, I guess the universe is not quite long enough, lasting, to make that possible. So we have to actually take a little bit of a shortcut here. We need to make buckets of documents that might have matches. In this case, for example, we could say, let's use the date of birth as the bucketing criterion and compare only people who have the same date of birth. That is actually a much smaller set. For a company with maybe 1 million customers, it turns out that you have a couple of hundred people born on the same date on the average. And so you compare those, much easier. The problem is, of course, what happens if the birth date is wrong? If two people are actually the same, but they have different birth dates? And the answer is, you just try another criterion. When you group by birth dates, you're going to pick up certain matches and you're going to miss others. But then you use a different kind of criterion, for example, the zip code, to actually find other matches. So it's additive. The more and more you test with different kinds of criteria, the better you get. So in order to find a good bucketing criterion, you got to have something that gives you no more than about 5,000 documents in a bucket. So birth date for companies with maybe 1 million customers is a very, very excellent choice. You could use something like the zip code, or you might get fancy. You could say, let's take the first 3 letters of the last name. By this, you effectively assume that those 3 letters are actually correct, and then you compare everything else. And then you do another pass where you take the first 3 letters of the first name, and so on. So this is how you partition the search space and find your matches within there. Our default is you can choose any attribute. That's one of the few things you need to specify. What is your bucketing criterion? What do you want to use? And then, after we have found the matches, after we have realized that 2 people are actually the same, we need to do truthification. Sometimes this is also called survivorship. So we need to find out among several different values which is the likely correct one. Usually it's very simple. You can use majority. So when more than one system agrees that somebody is called this and that, then that is probably the right value. You can assign weights to systems where you say this system is particularly good because it comes from a reliable database. There is another system where we have actually handwritten notes that were transcribed, so we may have less reliable data in there. So you can assign weights to the systems. We can also use other criteria to find the best values. For example, we could use the most recent value and assume that is correct. We can use a list of values where several values are actually all taken into the master rather than just one of them. And the default in our system is that we use a simple majority rule and we use equal weights for all source systems, but that is actually easily adjustable. So what does this look like in JavaScript? It's a small JavaScript module that can run in Stitch, and there is a couple of configuration variables on top of that. And this is what they look like, right? The first thing you got to specify is your discriminator. What attribute of your documents are the bucketing criterion? In this case, for example, it's the date of birth in the records. Then we need to specify what the distance function should be. We have a default function that is set by default. And then there is a distance threshold that says if documents are less than 0.1 apart, then we consider that person the same. So every single string attribute in the document is considered. We use the Levenstein distance on those, and every attribute has the same weight. And then finally, we have the truthification function. That function performs a simple majority selection on all the string attributes in the data. So whichever has the most votes is the one that wins. But you can actually become more fancier just by customizing that a little bit. You can see here distance fields and truthify fields, they are null, and you can specify your own values there. In this case, for example, distance fields. We choose first name and last name, and we give them weights of 0.4 and 0.6 respectively, which means that the first name is worth a little less than the last name. So if the last name of 2 people is similar, that counts a little more than if it's the first name. And then if you look at the truthify fields at the bottom, these are some more elaborate rules how we choose the survivor, how we find the truth. For example, for first name and last name, we give weights for the different 3 source systems. We got 3 systems, A, B, and C, and system A has a weight of 1, system B has a weight of 2, and system C has a weight of 0 for the first name. Very erroneous data, we don't trust that. And last name has a weight of 1 for system C. So we trust that a little more. And then we got a totally different algorithm for email. There is a selector function that is called select all, and that simply means I want every single email that I see in any of the source systems to be put into a list, and that's what I want to be my master criterion. So this is how you would customize that. The whole thing with a couple hundred lines of code goes into a stitch module, and then you have a couple of entry points to that. One way to use it is to actually have a sweep function. This is nothing but a cron trigger in Stitch, which calls this function, this module, once every 60 seconds and performs a regular pass over all of the documents. If you have millions of customers in there, that can take minutes, it can take hours to complete a pass, but we're doing that in work units of 60 seconds each. After 60 seconds, we checkpoint whatever we have achieved so far. The next time we get called, maybe right in the next minute, we do another 60 seconds worth of work, and then we checkpoint again, and so on. The second way to use the system is to perform a delta load. So you may put new documents, changes to existing documents into a source collection. That source collection will be carried over into the master collection, and we perform the matching process there again. We do have a REST API. With this REST API, you can give a single document to the module and say, figure out a match for this document and put it into that master record, and that's what it's going to do. And also we have a web UI on top of it, which allows you to display the contents of this master data set, to search within it, and to actually modify the data individually. And that is actually what we're going to see now. I'm going to hand it back to Britton, and Britton is going to show you the system live. Thank you.
Hello, and welcome back to the customer single view demo. We're actually going to take a look at different things. We're going to talk about the batch files, REST APIs, and admin consoles. We're going to go ahead and take a look at this process. One of the things that we're going to do is we're going to actually add a new source information through a REST-based API. We're going to verify that the record was mastered correctly, and then we're going to query that master record through the REST API. And then we're going to check the opt-out and verify that the data was scrubbed. And then if the customer comes back and says, oh, by the way, I'd like to opt back in, if they have their account ID, they can rehydrate that one source system at a time. So we're going to show a demo. This is a working prototype that we have that solves these issues. Again, this addresses some serious issues with consumer privacy and security. It auto-scales. It's hosted serverlessly. And so it's a fun demo to actually see. So we're going to go ahead and go out into the demo mode. And what I've brought up here is the admin console. This is nothing more than JavaScript and dynamic HTML. You could use the same concepts and build this in React or Angular or however you choose to develop. The nice thing about this is that this is able to be hosted on Stitch, or now it's going to be rebranded as Realm. But let's take a look at the page source. I'm able to actually go through and take a look at the key components where I'm actually including the Stitch SDK. And this allows me to log in. And in this particular case, I'm using a API credential. You can use Java Web Tokens. You can use third-party authorization like Google or Facebook, or you can actually have your own SSO that you want to connect in. All of these are available with Stitch. In this particular case, I've just put the user API key credential. This is not how you do it, but just for the demo, I put it in, connecting to my default client application, and then I'm actually creating a connection to the database and within MongoDB Atlas. And then I log in with my credentials. After I do that, I have a function called display customers, and I'm able to go through and look for all the different elements, the customer ID, the source, the ID, the phone, first name, last name, middle name, gender, date of birth, and I build a search document off of that. And then I simply do a find, where I actually go in and do a find. I pass in the search doc, and it pulls back the information. That's a lot of information to see on a particular thing, but this entire application is one page of code, very straightforward. Here we are with the first name and last name. Maybe I'm looking for anyone named Marion. Do a search. And we have lots of Marians. I'm looking for someone whose last name is Cole. I can search up this information, and I do have one Marion Cole. I have the date of birth, I've got contact phone, lots of personally identifiable information, and I can see that she exists in A, B, C, and D systems, and we can see that there are some different address information, and we can see that she is actually currently mastered, and she's at Hollywood. So the Hollywood is the actual address that we want. What we're going to do is add her to system E, for example, and we're going to update the address information to see one of the things that we used for the rules to apply. You can weight it from different systems, but you can also specify, since data gets stale quickly, that the last write wins, and that's what we've done in this particular case. So we're going to go and take a look at this particular API call, and we're going to update her system information. And we're going to put her in system E, and she has a new address, West Avenue in Hollywood, California. And I'll just give her a new zip code. And so phone number and everything else has stayed the same. We could give her a new email address. And all this information is now going to be inserted with a new system E information. And then I'm going to give it some random numbers, simulating a new unique ID being put into the system. When I send this information in, I might as well change, just to make it a challenge. Her middle name is Betty instead of Anita. And we'll send this off and see if it does get mastered correctly. And so it shows that the data was modified. We're going to go back and do a search again for Marion Cole. And we're going to edit this information. And we can see system E is here. And Anita, Annie, Betty, apparently people have misunderstood her name. It was in fact Betty. And we can see that it has been mastered correctly with the most recent date. Which is great. We can also see if we wanted to get system E or system D information, we can send this off like so, and we actually get her master address here, and then we get all of the subsystem information for the sources, system B, and that information sent back to the calling application as a document. Again, this was through a webhook, which is a hosted REST endpoint, and we're using the REST API. A post with a document coming in and a document going out. Now let's say that she does want to opt out. She has decided that she no longer wants to be in the system, and all of this trouble that we would have gone to scrub across all of these different systems and all of the compliance and security and everything is now going to be handled in one fell swoop. We simply opt out. We say yes, true. It shows that a modification has occurred. And we could actually run this query again. The interesting thing is, I'm going to go ahead and take the system E identifier, because when I search for Marion Cole, and she wants to verify that she has been removed, no data is returned. But if I take a look at sources, or I'm not sure if it's source ID. Let's take a look. If I could just go off that source ID, paste that in, and I'm just simply modifying the search document to give me the information that I need. I'm going to see if I can get that information back for this record. No, I did not. So let's go back and take a look at what we have here under that particular source ID without the username. And we do have everything set up to be undefined. In other words, the data has been scrubbed. Let's see if we can see how that works here. I want to make sure that I got it correctly, and it may be sources ID. There we go. And so same information comes back here. I can see that the document has all this information. So let's say that the last thing that she did was she bought a set of tires, she got the extended warranty, and then she ran over a nail. And she comes in and says, I bought the warranty, please replace my tires free of charge. And they're like, we can't find you in the system. We have no idea who you are or any of that information. So she's able to actually opt back in. We go back over here, and I want to get back in. I can set this flag to false, and she provides us this information again. When we send this information off, it will find her based on the account ID, and then we can actually go back in the back office system and query that information and find her. Or we could search by first and last name for that and replace her tires. Now, she was scrubbed out of the other systems, and after her tires are replaced, she may decide to opt out again. It's a very simple matter of opting in and opting out. So she opts back out, and this information is now refreshed. We can actually go back and take a look, and it's all cleansed again. So again, just the account ID, should she decide to opt in and opt out as many times as she likes in the day, it's a piece of cake. It's not a $14 million job with 10 DBAs. It's a simple update to a single view system. And I hope that this has been educational and informative, and I hope this has answered many of the questions that you have. There may be another demo to follow this using a batch process, but as we're doing this in real time, the same logic is used to actually go and load in batch files from multiple different systems. Source data can come in from a system in real time, or it can be batch processed on a nightly batch, for example. And again, opting in and opting out is very straightforward. And so we do have in these links, these are links that you can play with. You can actually go out there and hit these links and find a place to go and play with the data and see how this looks in real time. Also, we do have some single view use cases. This is actually before we went serverless. So these are actual, in some cases on premises, but they do use the same concepts that we have for mastering data across multiple different systems and providing a single view. MetLife is one of our good proof points, Experian Health, Humana, Alight, DHL, Air France. Groupe Renault actually did this on products. So they did it a 360-degree view of a car. So you can do single views of product information, single views of customer information, and have that same logic applied across multiple systems. And now that we have it serverless, we're hoping that this will lead to new products, new developments on-prem in the cloud and serverless for multiple customers that are out there trying to solve these problems. Again, thank you for your time. I hope that this kind of brings home the points as to why this is important, the problems that it solves, the CCPA, privacy, and being able to identify a customer across multiple systems. Just that information alone, if you're trying to do a marketing for everyone that had service or has a particular vehicle or has a particular attribute, it's a very easy way to get this information and contact your customers. Thank you very much for your time, and I hope that you enjoy the rest of mongodb.live. Thank you.